January 1940. A thin layer of frost rests over the fields of Iowa. The soil is dark, heavy, and still. Corn stalks from the previous harvest stand broken against the wind. There is no sound except the distant hum of a tractor idling in the cold. The war in Europe has already begun. Poland has fallen. France is uncertain. Britain braces itself. But here, across the American Midwest, the crisis is quieter. It lies beneath the surface. For decades, farmers have pulled harvest after harvest from this land. Corn, wheat, soybeans. The Great Depression forced them to produce more with less. Soil conservation programs slowed erosion. But the nutrients, nitrogen, phosphorus, potassium, have been steadily drained away. America is not yet at war. Yet if war comes, it will not only demand tanks and rifles. It will demand food, millions of tons of it. And in 1940, the United States does not have a stable domestic system for synthetic chemical fertilizers capable of sustaining that scale. The problem is buried in the soil, and it is about to surface. In 1940, the United States stood at a strange intersection of abundance and vulnerability. On paper, America was an agricultural giant. Its wheat fields stretched across Kansas and the Dakotas. Its corn belt ran through Iowa, Illinois, and Indiana. Cotton dominated the South. Livestock numbers were immense. The nation exported grain to Europe even as war spread across that continent. Yet beneath this appearance of strength lay a structural weakness that policymakers understood, but the public rarely considered. Modern high-yield farming depends on nitrogen. And nitrogen, though abundant in the atmosphere, cannot be used directly by crops. It must be fixed into ammonia or nitrate compounds before plants can absorb it. Before World War I, much of the world's usable nitrate came from one place, Chile. The Atacama Desert contained massive natural sodium nitrate deposits. These Chile saltpeter reserves fed global agriculture and supplied explosives factories. The same compound that made wheat grow also made artillery shells detonate. The First World War changed everything. Germany, cut off from Chilean imports by the British naval blockade, turned to industrial chemistry. Using the Haber-Bosch process, developed in the early 20th century by Fritz Haber and Karl Bosch, German industry synthesized ammonia from atmospheric nitrogen. This innovation allowed Germany to sustain both munitions production and agricultural output despite blockade conditions. The lesson was clear to every major power. Nitrogen was strategic. After 1918, the United States expanded some domestic nitrogen production capacity, primarily through government-backed facilities like the nitrate plants at Muscle Shoals, Alabama. But peacetime economics reshaped priorities. Imported Chilean nitrate was often cheaper than domestically synthesized ammonia. Private industry invested cautiously. By the late 1930s, America's fertilizer industry was growing, but it was not yet structured for total war demand. Production remained fragmented. Much nitrogen capacity was still tied to munitions heritage plants or small-scale chemical operations. The agricultural system depended heavily on a mix of imported nitrates, natural soil fertility, crop rotation, manure, and limited synthetic inputs. Then came the Great Depression. From 1929 through much of the 1930s, farm prices collapsed. Wheat, corn, and cotton values plummeted. Farmers intensified production in an attempt to survive falling prices. In many regions, land was pushed harder than ever before. Soil depletion accelerated. At the same time, environmental catastrophe struck the Great Plains. Between 1930 and 1936, the Dust Bowl revealed the cost of poor soil management. Wind erosion stripped away topsoil across millions of acres. The federal government responded with conservation programs, counter-plowing initiatives, and the creation of the Soil Conservation Service in 1935. But conservation alone could not restore nutrient balance. Nitrogen removed through repeated harvests had to be replaced. By 1939, Europe was at war again. Germany invaded Poland on September 1st. Britain and France declared war 2 days later. American neutrality remained official, but economic reality shifted. The United States began expanding industrial output in anticipation of possible involvement. War planners within the War Department and the Department of Agriculture understood a central principle: armies march on food. Modern mechanized armies require more calories than those of previous centuries. Millions of soldiers must be fed daily. Industrial workers must be fed to sustain weapons production. Allies may depend on American grain shipments. Food became part of strategic planning. In 1940, U.S. agricultural production was strong, but not infinitely elastic. Crop yields depended heavily on weather and soil condition. Without expanded fertilizer inputs, yield increases would be limited. Natural manure supplies from livestock could not scale quickly. Crop rotation with legumes helped replenish nitrogen, but acreage devoted to legumes reduced acreage available for grain. If war mobilization demanded dramatic increases in wheat, corn, and livestock feed production, nitrogen would become the limiting factor. Meanwhile, global trade routes were uncertain. The Atlantic was increasingly dangerous. German U-boats targeted shipping. If imports of Chilean nitrate were disrupted, American agriculture would face constraints precisely when demand surged. Chemical companies observed these signals closely. Firms like DuPont, Allied Chemical, American Cyanamid, and Monsanto were already involved in industrial chemical production. Their expertise ranged from sulfuric acid to phosphates, from industrial solvents to synthetic intermediates. They understood ammonia synthesis. They understood scale. Monsanto, founded in 1901 in St. Louis, had built its business initially on saccharin and industrial chemicals. By the 1930s, it had expanded into sulfuric acid, phosphates, and other chemical inputs critical to fertilizer production. It was not yet the agricultural biotechnology giant it would later become, but it was firmly embedded in American industrial chemistry. As Europe burned, American industry began preparing quietly. The National Defense Advisory Commission was established in May 1940 to coordinate industrial preparedness. Discussions intensified around strategic materials: steel, aluminum, rubber, oil. Food rarely made headlines, but inside policy rooms, fertilizer capacity was recognized as foundational. Because without nitrogen, there would be no grain surplus. And without grain, there would be no sustained war effort. By late 1940, the question was no longer theoretical. It was logistical. How quickly could the United States expand synthetic nitrogen production? How many ammonia plants would be required? Which companies had the technical capacity? The soil of the Midwest held the answer, but the factories of America would determine whether it could be unlocked. While American planners assessed vulnerability, Germany had already solved its nitrogen problem 2 decades earlier. The Haber-Bosch process, industrialized before the First World War, allowed atmospheric nitrogen to be converted into ammonia under high temperature and pressure using iron catalysts. By the 1930s, German chemical conglomerates, particularly IG Farben, had mastered large-scale synthetic production. For the Third Reich, nitrogen was not simply agricultural input. It was strategic oxygen for war. Ammonia fed fertilizer plants. It also fed nitric acid production. Nitric acid fed explosives manufacturing, TNT, nitroglycerin propellants. The same industrial backbone sustained both bread and bombs. When Germany rearmed under Adolf Hitler, it did so with full awareness that blockades had nearly strangled it in 1914 to 1918. This time, synthetic chemistry would prevent that weakness. By 1939, Germany possessed one of the most advanced integrated chemical industries in the world. The United States had industrial capability, but it had not yet mobilized it in the same centralized way. American chemical production in 1940 was substantial, yet diversified across civilian markets. Ammonia was produced, but not at a scale optimized for massive wartime agriculture combined with explosive demand. Much of the existing capacity was distributed regionally, dependent on natural gas feedstocks, and tied to private sector economics rather than national defense priorities. Furthermore, fertilizer use in American farming was uneven. In the Southeast, phosphate fertilizers were more common, particularly for cotton. In the Corn Belt, reliance on crop rotation and livestock manure remained widespread. Synthetic nitrogen usage was increasing, but not yet universal. This meant yields were vulnerable to expansion limits. When President Franklin D. Roosevelt began accelerating defense production in 1940, especially after the fall of France in June, the logic became urgent. Britain stood alone against Germany. If the United States were to become the arsenal of democracy, it would also need to become its granary. In September 1940, the United States enacted the Selective Training and Service Act, the first peacetime draft in American history. Military expansion was no longer abstract. Troop numbers would climb. Training camps would multiply. Shipyards and aircraft factories would expand. Every additional soldier required approximately 3,000 calories per day. Industrial laborers required similar intake. Allied support under the Lend-Lease program, enacted in March 1941, would add further strain. Grain exports to Britain increased sharply. Agricultural production targets rose accordingly. To meet them, yield per acre had to increase. There was limited room to expand cultivated land rapidly without environmental consequences. Mechanization had improved efficiency, but soil chemistry imposed hard boundaries. Nitrogen became central to planning documents within both the Department of Agriculture and the War Department. The same facilities capable of producing ammonia for fertilizer could be converted to produce nitric acid for explosives. In wartime, these two functions would operate in tandem. This dual-use characteristic changed everything. Companies that could produce ammonia were no longer simply fertilizer suppliers. They became strategic industrial partners. Monsanto was positioned inside this transformation. By 1940, the company operated major facilities in St. Louis and elsewhere, producing sulfuric acid, phosphates, and other industrial chemicals essential to fertilizer manufacturing. Sulfuric acid, in particular, was a cornerstone of chemical processing, used in phosphate fertilizer production and in numerous wartime chemical reactions. As defense planning intensified, chemical companies were drawn into closer coordination with federal authorities. The creation of the Office of Production Management in January 1941, later reorganized into the War Production Board in 1942, formalized industrial mobilization. Contracts would expand. Facilities would scale. The United States had natural gas reserves, particularly in Texas, Oklahoma, and Louisiana, that provided feedstock for ammonia synthesis. What it lacked was rapid, centralized expansion of plants specifically designed for high-volume nitrogen fixation under wartime urgency. Germany had built such infrastructure over years of rearmament. The United States would need to compress that timeline dramatically. The stakes were unmistakable. If fertilizer production lagged, crop yields would plateau. If yields plateaued, food supplies for troops and allies would tighten. If ammonia plants focused exclusively on munitions, agriculture could suffer. If they focused exclusively on fertilizer, explosive output might slow. Balance had to be engineered, chemically and administratively. By late 1940 and early 1941, as Congress debated aid to Britain and American factories ramped up aircraft, tanks, and ships, chemical executives and federal planners confronted the quiet arithmetic of nitrogen. Atmospheric nitrogen was infinite. Usable nitrogen was not. To convert air into sustenance and into firepower required pressure vessels, catalysts, pipelines, rail networks, trained chemists, and capital. It required industry to pivot from peacetime calculation to wartime scale. And as 1941 approached, the soil of America waited for what the factories would do. In the spring of 1941, farmers across the Midwest prepared their fields with a cautious optimism. Tractors had replaced horses in many counties. Hybrid corn varieties were spreading. Federal price supports offered some stability after the devastation of the Depression. But beneath the mechanical improvements lay a biological truth. Each harvest removed nutrients. Every bushel of corn carried nitrogen out of the soil. Every bale of cotton stripped phosphates from the ground. Farmers understood fertility in practical terms. They rotated crops. They planted legumes like clover and alfalfa to restore nitrogen naturally. They spread manure. But these methods required time, livestock, and acreage that might otherwise produce food grain. As defense contracts expanded and crop demand projections rose, extension agents from the Department of Agriculture began encouraging increased fertilizer use. Bulletins circulated. Demonstration plots showed yield differences between fertilized and unfertilized fields. For many farmers, synthetic nitrogen was still an expense weighed carefully against uncertain markets. But as war orders expanded and grain prices strengthened, fertilizer became less of a gamble and more of a necessity. The pressure was not dramatic or theatrical. It was steady. More bushels per acre, more feed for livestock, more wheat for export. The farmer's relationship with soil shifted subtly. Fertility was no longer just stewardship. It was production capacity. And production capacity was becoming a matter of national security. Military planners think in tonnage. In 1941, as the U.S. Army expanded from a modest peacetime force to a rapidly growing mobilized institution, logistics officers calculated not only ammunition and fuel but rations. Standard Army field rations included flour, canned meat, dehydrated vegetables, sugar, and coffee. Each component traced back to American farms. By the time the United States formally entered the war after December 7, 1941, these calculations accelerated. Millions of troops would eventually serve overseas. Allied nations, particularly Britain and later the Soviet Union, depended on American agricultural exports under Lend-Lease. In 1942 alone, U.S. agricultural exports surged dramatically compared to pre-war levels. Wheat shipments increased. Pork and beef output rose. Dairy production expanded. This expansion required feed grain. Feed grain required nitrogen. Without sufficient fertilizer, acreage expansion alone could not guarantee yield growth. Weather remained unpredictable. Soil nutrient limitations were measurable. War planners understood that relying solely on favorable rainfall was not strategy. Food security was integrated into military planning documents. The War Production Board, established in January 1942, coordinated industrial priorities, and fertilizer production was included among controlled materials. The tactical logic was direct. More nitrogen, higher yields, more food sustained armies. The chain extended from ammonia reactor vessels to infantry rations thousands of miles away. The battlefield began in the field. The Haber-Bosch process operates under extremes. Nitrogen and hydrogen gases are combined at temperatures approaching 400 to 500 degrees Celsius and pressures often exceeding 150 to 200 atmospheres. Iron-based catalysts accelerate the reaction. The output is ammonia, NH3, a simple molecule with immense strategic value. Hydrogen is typically derived from natural gas through steam reforming. Nitrogen is separated from air. The process requires large compressors, high-pressure steel vessels, precise engineering, and steady energy input. Scaling such facilities is not trivial. Plants require months, sometimes years, to design and construct. Skilled chemical engineers and metallurgists are essential. By 1940 to 1942, American industry accelerated construction of synthetic ammonia plants across several states, particularly near natural gas supplies. These plants were designed with dual capacity in mind: fertilizer production and nitric acid feedstock for explosives. Monsanto and other chemical firms expanded sulfuric acid and related chemical outputs, enabling downstream fertilizer manufacturing. Industrial integration deepened. Phosphate rock mining increased. Transportation networks were coordinated to move both raw materials and finished fertilizers efficiently to farming regions. Technology did not merely support agriculture. It reshaped it. The soil was no longer solely dependent on biological cycles. It became linked to high-pressure reactors, pipelines, and chemical laboratories. Air was compressed. Molecules rearranged. Atmosphere transformed into grain. But technology alone could not define the outcome. It depended on leadership, coordination, and industrial will, factors that would shape the next dimension of this transformation. By 1941, industrial mobilization was no longer theoretical. Contracts were issued. Blueprints were drafted. Steel allocations were assigned by priority code. Chemical executives found themselves operating inside a new framework. The federal government did not nationalize the industry outright, but it directed it. Production targets were coordinated through agencies that balanced fertilizer, explosives, and other strategic materials. Monsanto was part of this coordination network. The company had already established itself as a major producer of sulfuric acid, one of the most widely used industrial chemicals in the world. Sulfuric acid was essential in phosphate fertilizer production. It was also indispensable in explosives chemistry. As wartime demand increased, sulfuric acid output expanded significantly across the United States. Facilities ran longer shifts. Capacity additions were approved. Rail shipments increased in volume and frequency. Leadership decisions became technical and moral at once. If ammonia was diverted too heavily toward nitric acid for munitions, fertilizer supply could tighten. If fertilizer production lagged, crop yields might falter. The solution was expansion, not substitution. New ammonia plants were constructed near Gulf Coast natural gas supplies. Existing facilities were upgraded. Catalysts were improved. Pressure vessel metallurgy advanced under wartime research funding. The chemical industry demonstrated a capacity to scale rapidly when aligned with federal coordination. This scaling was not chaotic. It followed allocation systems designed to prevent bottlenecks. For companies like Monsanto, this period marked a transformation. They were no longer only suppliers to private markets. They were participants in a national survival network. Industrial leadership meant maintaining output stability despite labor shortages, transportation strain, and material rationing. It meant synchronizing fertilizer deliveries with planting seasons while fulfilling munitions-related chemical contracts. The factories did not produce headlines. They produced molecules. But those molecules were becoming strategic assets. Germany's chemical complex, particularly IG Farben, had demonstrated before the war how synthetic chemistry could underpin military autonomy. By the late 1930s, Germany's nitrogen fixation capacity supported both agriculture and armament production at scale. American planners studied this precedent closely. The First World War had already proven that blockades could restrict nitrate imports. Germany's answer had been industrial chemistry. Now the United States faced the inverse challenge. It possessed abundant natural resources and geographic insulation, but it needed rapid mobilization. The American advantage lay in natural gas reserves and industrial diversity. Unlike Germany, which lacked many raw materials and pursued synthetic substitutes for fuel and rubber, the United States had direct access to energy feedstocks required for ammonia synthesis. Yet infrastructure had to be expanded. The comparison sharpened urgency. Germany had integrated its chemical industry into state planning years before open war. The United States compressed that integration into a shorter window between 1940 and 1942. By 1943, American ammonia production capacity had expanded dramatically compared to pre-war levels. This growth supported not only domestic agriculture, but also explosive manufacturing required for Allied offensives in North Africa, Italy, and eventually Western Europe. Chemical strength became a quiet form of superiority. The nation that could convert air into both food and firepower efficiently held strategic resilience. America's industrial expansion in nitrogen fixation and related chemicals ensured that it would not face the same vulnerability that had once haunted European powers. And this industrial confidence carried consequences beyond the battlefield. Wartime urgency accelerated technological adoption. Farmers who might once have hesitated to rely heavily on synthetic fertilizers increasingly integrated them into standard practice. Government campaigns encouraged maximum yield. Posters urged farmers to produce food for freedom. The psychological shift was subtle but permanent. Soil fertility, once governed primarily by crop cycles and animal husbandry, became increasingly dependent on industrial inputs. The link between chemical factories and farmland strengthened. After the war, the infrastructure built for nitrogen production did not disappear. Instead, surplus capacity flowed into civilian agriculture. Fertilizer usage per acre rose steadily in the post-war decades. Yields climbed correspondingly. This transformation supported population growth and global food exports. It also introduced environmental consequences that would only become widely debated decades later: runoff, waterway eutrophication, and soil chemistry imbalances. But in the early 1940s, those long-term effects were distant. The immediate imperative was survival and victory. Chemical fertilizer became normalized not as emergency support, but as a foundational tool of modern agriculture. Monsanto and other chemical firms expanded beyond wartime supply roles into broader agricultural markets. Their identity shifted. They were no longer peripheral industrial suppliers. They were integrated into the agricultural future of the nation. The soil of 1940 was finite in its natural nitrogen. The atmosphere above it was infinite. Wartime industry bridged the gap between the two, and that bridge would carry the nation toward a decisive turning point once war fully engulfed. December 7th, 1941. At 7:55 a.m., Japanese aircraft attacked Pearl Harbor. Within hours, the United States was at war. Within days, Germany and Italy declared war on America. The industrial calculations of 1940 became immediate national imperatives. Mobilization accelerated beyond anything previously attempted in American history. Factories that had been expanding cautiously now moved at full speed. Steel production surged. Shipyards multiplied output. Aircraft plants ran around the clock. And quietly, behind headlines of tanks and bombers, ammonia reactors increased pressure. The War Production Board, formally established in January 1942, assumed authority over material allocation. It issued directives that balanced competing demands: aluminum for aircraft, copper for wiring, steel for ships. Nitrogen compounds entered this system as both agricultural necessity and explosive precursor. Ammonia was directed toward two streams. One flowed into fertilizer production for the 1942 planting season. The other flowed into nitric acid plants that fed munitions factories manufacturing TNT and propellants. The dual-use tension reached its most intense phase in early 1942. Military planners feared food shortages if fertilizer application fell behind. Simultaneously, ordnance departments demanded expanded explosive output to supply new divisions deploying overseas. The solution was expansion rather than rationing. New government-financed ammonia plants were authorized, often constructed with private operators managing production under federal contract. Locations were selected near natural gas fields along the Gulf Coast and in parts of the Midwest. High-pressure equipment orders were prioritized. Skilled chemists were redirected from civilian research into plant operations. Monsanto and peer chemical firms expanded sulfuric acid output, an essential ingredient for processing phosphate fertilizers and various wartime chemicals. Rail networks coordinated shipment schedules to ensure fertilizer reached farming regions before spring planting windows closed. Time became critical. In agriculture, delays are not abstract. Missing a planting window by weeks can reduce yields dramatically. War planners could not afford a lost season. The 1942 crop year thus became a test of industrial agricultural synchronization. Government campaigns encouraged farmers to maximize acreage. Labor shortages emerged as young men entered military service. The Women's Land Army and other civilian labor initiatives helped fill gaps. Mechanization increased where possible, but none of it mattered if soil nutrients were insufficient. By mid-1942, fertilizer production levels had risen compared to pre-war years, despite simultaneous explosive manufacturing demands. It was an early indicator that American industrial capacity could expand in parallel streams rather than at zero-sum expense. Statistics from wartime production reports show steady increases in nitrogen output through 1942 and 1943. While exact allocation figures varied month to month, total synthetic ammonia capacity expanded significantly compared to 1940 baselines. The battlefield consequences were indirect but real. In North Africa, U.S. forces engaged Axis troops in late 1942. In Britain, American troops prepared for eventual cross-channel invasion. In the Pacific, island campaigns demanded sustained logistical chains across vast distances. Every deployment depended on caloric continuity. Back in the Midwest, combines harvested corn that had grown taller and fuller because nitrogen had been applied at scale. Wheat shipments left ports bound for allied nations. Pork production increased as feed supplies remained stable. The connection between reactor vessel and rifleman was invisible but unbroken. Yet the strain was not over. As 1943 approached, Allied offensives expanded. Munitions demand intensified. Nitric acid production climbed sharply to support artillery shells and aerial bombs. Ammonia plants ran near capacity. The system had proven it could expand once. Now it would be tested under sustained maximum load. And in that sustained pressure, chemical, industrial, strategic, the decisive balance between bread and bullets would reach its most critical point. By 1943, the United States was fighting on multiple fronts. In North Africa, Allied forces pushed east after Operation Torch. In the Pacific, brutal campaigns unfolded across Guadalcanal and New Guinea. Strategic bombing intensified over Europe. Each offensive required staggering quantities of munitions. Artillery shells consumed nitrates. Bombs required nitric acid. Propellants demanded precise chemical mixtures derived from ammonia feedstocks. At the same time, agricultural targets did not decline. They increased. The U.S. Department of Agriculture launched the Food for Freedom campaign, urging farmers to exceed previous output records. Posters and radio broadcasts framed agricultural production as direct participation in the war effort. The numbers reflected that urgency. Between 1940 and 1944, U.S. agricultural production rose substantially. Corn output increased. Wheat harvest expanded. Meat production climbed as livestock feeding intensified. These gains were driven by mechanization, improved seed varieties, expanded acreage, and, critically, increased fertilizer use. Synthetic nitrogen application rose steadily throughout the war years. Though exact regional usage varied, national production capacity for ammonia and related nitrogen compounds had expanded well beyond its 1940 level by 1943 to 1944. The decisive test came not in a single battle, but in sustained continuity. Allied offensives in 1944 required unprecedented logistical coordination. In June 1944, Operation Overlord, the D-Day landings in Normandy, began. The invasion required months of stockpiling food, ammunition, fuel, and medical supplies in Britain before the assault. American grain shipments to Britain and other Allied nations remained consistent. Meat supplies held steady. Rationing existed domestically, but widespread famine was avoided. Behind these outcomes stood industrial chemistry operating at scale. Ammonia plants functioned near full capacity. Nitric acid production reached high wartime levels to support ordnance manufacturing. Fertilizer deliveries to farmers were maintained through careful allocation planning. Railroads operated under heavy strain, moving both military cargo and agricultural inputs. The War Production Board's coordination mechanisms proved capable of preventing catastrophic shortages. When bottlenecks emerged in rail transport, sulfur supply, or natural gas distribution, adjustments were implemented through centralized planning. Monsanto and other chemical firms operated within this tightly managed framework. Their facilities contributed sulfuric acid and related chemical intermediates critical to fertilizer processing and wartime production chains. The system did not collapse under competing demands. Instead, it demonstrated a structural strength rooted in expansion capacity and resource abundance. Unlike Germany, which increasingly faced resource shortages as Allied bombing campaigns targeted synthetic fuel and chemical plants, the United States operated largely free from domestic industrial disruption. American ammonia plants were not under aerial bombardment. Rail lines were not severed by invading armies. Natural gas supplies flowed uninterrupted. By late 1944 and in 1945, the balance between bread and bullets had stabilized. Explosives production supported final offensives into Germany. Agricultural output remained sufficient to sustain both domestic consumption and Allied needs. The war in Europe ended on May 8, 1945. In the Pacific, fighting continued until Japan's surrender on September 2, 1945. When the guns fell silent, the industrial infrastructure built under wartime urgency remained. Ammonia plants stood ready. Sulfuric acid facilities remained active. Phosphate processing operations were intact. What had been constructed to solve an immediate strategic vulnerability now formed the backbone of a transformed agricultural system. The turning point was not a single explosion or treaty signature. It was the moment when industrial nitrogen capacity exceeded emergency demand, when the United States realized it could sustain both maximal munitions output and record agricultural harvests simultaneously. That realization reshaped planning assumptions permanently. The soil no longer depended solely on biological cycles or imported nitrates. It was integrated into a national chemical network capable of converting atmospheric nitrogen into stability. War had accelerated the fusion of agriculture and industry. And when peace returned, that fusion would not dissolve. It would expand, carrying profound consequences for farmers, corporations, ecosystems, and global food systems in the decades ahead. September 1945. The war was over. Troop ships began returning home. Munitions contracts were canceled or reduced. Assembly lines slowed. Factories that had operated continuously for 4 years faced a new question. What now? The ammonia plants did not disappear. During the war, the United States had expanded synthetic nitrogen capacity dramatically. Facilities built or enlarged to meet explosive demand now stood with reactors capable of sustained high-pressure output. Nitric acid production, once prioritized for ordnance, no longer required the same volume. The chemical infrastructure had overshot peacetime agricultural demand. But peacetime demand was about to change. In 1940, many American farmers had used limited synthetic nitrogen. By 1945, fertilizer had proven itself as a yield multiplier under extreme national pressure. Farmers had witnessed harvest records achieved during wartime mobilization. The link between nitrogen application and production reliability had become clear. Post-war policy reinforced this transition. Federal agricultural programs encouraged productivity to stabilize prices and support both domestic consumption and exports. Europe, devastated by war, required food shipments during Reconstruction. American grain continued to flow abroad through relief programs. Surplus industrial nitrogen found a ready market. Ammonia production that had once fed explosives now flowed into fertilizer channels. Phosphate processing expanded. Distribution networks strengthened. Rail lines that had carried wartime cargo now transported fertilizer to rural cooperatives. Between the late 1940s and early 1950s, fertilizer consumption in the United States rose steadily. Nitrogen application per acre increased. Yields followed. Corn productivity climbed. Wheat harvests became more predictable. The war had normalized chemical dependency in agriculture. Companies like Monsanto transitioned smoothly from wartime chemical coordination to post-war agricultural markets. Their sulfuric acid and phosphate operations remained central to fertilizer manufacturing. Industrial expertise developed under emergency conditions became peacetime commercial advantage. The broader agricultural system also changed structurally. Mechanization continued. Tractors became standard. Hybrid seeds improved genetic yield potential. Irrigation expanded in Western states. Nitrogen became one of three essential pillars, alongside mechanization and genetics, supporting the modern American farm. But abundance carried its own dynamics. As yields rose, market prices sometimes fell. Surpluses accumulated. Federal storage programs managed excess grain. Export strategies expanded. The United States emerged not only as a military superpower, but as an agricultural one. The transformation had strategic implications beyond economics. Food security became part of Cold War diplomacy. Grain shipments functioned as political leverage. Agricultural productivity demonstrated industrial strength. The infrastructure built under the shadow of global conflict now projected influence across peacetime geopolitics. Yet beneath the rising harvest statistics, another layer of consequence was quietly forming. One less visible than victory parades, but embedded in soil and water systems that would take decades to fully understand. The post-war years brought prosperity to American agriculture, but they also deepened its dependence on industrial chemistry. By the early 1950s, synthetic nitrogen fertilizer had become a standard component of large-scale farming operations. What had once been an emergency expansion during wartime was now routine practice. Application rates increased steadily decade after decade. Yields rose accordingly. Corn production per acre climbed significantly compared to pre-war averages. Wheat yields improved. Livestock feeding became more intensive as feed grain supply stabilized. The United States entered a period often described as the beginning of modern industrial agriculture. Nitrogen was central to that transformation. The ammonia plants built during wartime did not idle. Instead, they operated at commercial scale. Natural gas remained the primary feedstock. Refinements in catalyst efficiency and plant engineering reduced costs over time. Production became more economical, making fertilizer more accessible to farmers. Monsanto, alongside other chemical manufacturers, expanded its agricultural product lines in the post-war era. Sulfuric acid production remained essential for phosphate fertilizer processing. Chemical companies deepened their integration into farming systems. What had been coordination with federal wartime agencies evolved into commercial partnerships with distributors, cooperatives, and growers. The soil was no longer only a biological system. It was part of an industrial network. By the late 1950s and 1960s, fertilizer use per acre had multiplied compared to 1940 levels. The United States became capable of producing enormous food surpluses. These surpluses supported population growth at home and food aid abroad. Globally, synthetic nitrogen would later underpin the Green Revolution, dramatically increasing yields in parts of Asia and Latin America. The scientific foundation for this revolution traced directly back to early 20th century nitrogen fixation, and its wartime scaling in the United States reinforced its reliability and availability. But consequences accumulated gradually. Nitrogen that plants did not absorb did not vanish. Rain carried excess nitrate into streams and rivers. Over decades, agricultural runoff contributed to nutrient loading in major waterways, including the Mississippi River system. Coastal ecosystems began experiencing seasonal oxygen depletion linked to fertilizer runoff, phenomena later studied and labeled as hypoxic zones. In the 1940s and 1950s, these environmental effects were not widely understood. The immediate post-war narrative focused on abundance, efficiency, and progress. Chemical fertilizers symbolized scientific mastery over natural limits. There was also economic consolidation. Larger farms adopted fertilizer-intensive practices more quickly. Mechanization and chemical inputs favored scale. Smaller operations sometimes struggled to compete. Rural demographics shifted gradually as agricultural efficiency reduced labor demand. The Industrial Agricultural Alliance forged during wartime did not dissolve. It matured. Monsanto, which had contributed to chemical supply chains during the war, evolved into a major player in agricultural chemistry in the decades that followed. Its growth reflected broader structural changes in American industry, where chemical innovation and farming became increasingly interconnected. The strategic logic of 1940 had been clear: ensure food supply under threat. The strategic reality of 1950 was different: manage abundance while sustaining profitability and global influence. The infrastructure that had once answered a wartime vulnerability now anchored an economic system. Nitrogen flowed continuously from atmosphere to reactor to field. The quiet, frost-covered soil of 1940 had become part of a global chemical cycle engineered by industry. And the long-term meaning of that transformation extended beyond production statistics, reaching into questions of sustainability, responsibility, and the enduring legacy of decisions made under the pressure of war. The war ended, but its imprint on the land endured. The soil that once relied on natural cycles now carried the imprint of human engineering. Nitrogen, once scarce in practical terms, flowed from industrial reactors into fields across the Midwest. The quiet expansion of chemical infrastructure during wartime had permanently altered agriculture. What began as a strategic necessity, ensuring that armies and allies could be fed, became the foundation of modern farming. America's ability to convert atmospheric nitrogen into sustenance created surpluses that reshaped domestic society, supported global relief efforts, and projected influence abroad. Monsanto and other chemical firms exemplified this transformation. Wartime contracts had forged an industrial capacity previously unimaginable in peacetime. After the war, these facilities continued to supply fertilizer, embedding chemical inputs into farming practices for decades. The broader lesson was one of connection. Industrial technology, policy planning, and human labor intertwined in ways that no single element could achieve alone. Soil fertility, once a matter of biology and patience, became a product of chemistry, logistics, and industrial foresight. Yet the transformation was double-edged. The same molecules that increased yield also introduced long-term environmental consequences. Fertilizer runoff would reshape rivers, estuaries, and ecosystems in ways that only future generations would fully measure. The silent costs of abundance were embedded in water and soil. Still, in the context of 1940, the results were decisive. American agriculture survived the stress of war, supported soldiers, nourished allies, and demonstrated the potential of industrialized food production. It proved that national security extended beyond guns and tanks, to fields, factories, and molecules invisible to the naked eye. The frost that once lay over Midwestern soil had been transformed into golden waves of grain, a tangible testament to planning, chemistry, and human resolve. In the end, the crisis of 1940 was not only a challenge of scarcity. It was the moment when the United States learned to convert necessity into capability, turning air into fertilizer, and fertilizer into both survival and strength. The soil remembered. The nation endured.